Now when you first align a helium neon laser like this, a very curious thing often occurs. If you look at the beam very, very carefully, you'll notice that the beam is not round and homogeneous, but consists of a series of patterns, oftentimes resembling those of a flower petal. These are called modes. They're actually called transverse electromagnetic modes, or TEM modes. The lowest order mode, 00, is the Gaussian mode, in which the brightest spot occurs dead center of the mode and it fans out in all directions equally. But other modes are allowed as well and oftentimes appear inside the laser. Let's take a look at some of these modes. When I first turn on the laser, this is what the beam actually looks like. In order to see it clearer, I'm using the output beam from the HR of the laser. It's a lot lower powered than the one coming out of the OC, and therefore allows the camera, or our eye, to focus on it a lot easier. So I've taken the HR output from my laser, I've let it travel approximately 2.5 meters, and intercepting it with this little white card here, so you can clearly see the pattern of the mode. This particular mode is a multi-mode. It is a high order mode of the laser, and it's giving me approximately 3.8 milliwatts of output power. In order to see a different mode, all I need to do is to change one or more of the mirror adjustments on this laser until I get a different mode. It changes the optical path inside the laser and therefore changes the way in which power is stored within the actual optical cavity itself. A small adjustment of the laser right now, and you can see a different mode. This particular mode looks like TEM01 donut mode. It's a circular mode in which there is a dark spot in the center and a dark spot around the outside. This is one of the only circular symmetry modes you'll get usually off a small laser like this. Oftentimes modes have rectangular symmetry, and they consist of a number of dots. This mode is a TEM01 mode as well, but in this case it's a rectangular TEM mode. When I draw two lines, one going this way and one going this way, I look at how many dark lines intersect. In this direction I have 0 dark lines. In this direction I have 1 dark line. So this is called TEM01, or if you prefer, TEM10. You see, there's no reference to absolute, which is X and which is Y axis. You can turn it any way you like. As a matter of fact, you'll notice that these modes are turned at approximately a 45-degree upwards. That's the way it usually exists. A few more simple adjustments and you'll notice all the number of modes that are possible. This one almost looks like a TEM02 circular mode, and that's a very rare mode to get. Of course, I should tell you this mode usually doesn't show up, but since I have a camera today, it's graced me with its presence. Here we see a TEM02 mode. Once again, in this direction, I have no dark lines. In this direction, I have 2 dark lines. So it's TEM02, or if you prefer, TEM20. The one thing thing that isn't evident right now from looking at these, although it is if you're in front of the laser looking at the power meter, is that the power varies greatly by the mode as well. Low order modes like TEM00 tend to have low powers, whereas higher order modes tend to have higher powers. This isn't exactly a rule. There are exceptions to it, of course, but generally speaking, you'll find that when you have more modes existing in the output of a laser, you'll tend to have higher powers on these lasers. The reason for this is simple. It's packing fraction. How well can you use the volume of the actual amplifier itself? A higher order mode with lots of little spots and dots in it can, generally speaking, use the amplifier's volume more efficiently. And they pack better inside the amplifier. And so you tend to get higher powers from those modes. To give you an idea from my own experiences, while lining up a carbon dioxide laser, I could achieve approximately 12 watts on the TEM00 mode, but when I went to a very high order mode, that being TEM34, I was able to get approximately 57 watts. So there's a huge difference in there. Mind you, some of these modes are desirable because they can focus better. The 00 mode focuses better than, for example, the TEM34. But it all depends on your specific application of your laser. One of the fundamental characteristics of a laser amplifier is the small signal gain. It's one of the most important characteristics that we can measure in this setup. And in order to do that, we're going to take our helium neon laser and put a variable loss inside of it. Now the variable loss in this case is a tilted glass slide. We put this slide right inside the cavity. It sits at an arbitrary angle in this case, and our power is displayed on here. When we're at Brewster's angle, logically speaking, we get the maximum output power on the meter. When we're at any other angle, we're going to get a decreasing output until finally the loss, the reflection loss of each surface of this glass makes the total loss of everything inside this laser larger than the gain. Measurement of gain is oftentimes done this way. You take a variable loss of some type and you increase that loss until the point where it barely oscillates. And in this case, you'll notice I'm getting an output power of approximately, maybe 100 microwatts. That's what we call small signal. And at this point, if I add the losses inside the laser altogether, that includes the loss of the HR, the loss of the OC, the loss due to attenuation, the loss due to these windows, and finally the loss of that slide, which I can now calculate. I add those losses together and I now equate it to gain, or G0, the small signal gain of the amplifier. Now the first parameter I'm going to want to know is the index of refraction of this slide. I already kind of know what it is, but it's always nice to measure it. So the first thing I'm going to do is set this thing so it's perfectly perpendicular to get my 0 angle. In order to do this, I simply vibrate this slide rapidly until I get a very small dot, and I can see the dot on the actual output coupler. And once that dot lines up with the optical axis, I can call that 0. And in this case, I'm reading it at 18.5 degrees on the actual rotary stage. Now I simply rotate this glass slide, and at some point it starts to oscillate. And I'm now getting output from the laser, and I increase it as much as I can. So I'm slowly increasing it. I'm up around I went too far. It was up around 2.4 milliwatts, and then the power started to go down. So go back to where the maximum power exists, right around there, and I read the angle as 320 degrees. So 320, that's 40 plus 18.5 for the offset. That makes 58.5 degrees. That's theta Brewster in this case, and from there I can now calculate the index of refraction of that slide. Now while I have this set up, let's measure the gain. Brewster's angle will obviously give me the maximum power output because it's giving me zero loss in one polarization. What I'm going to do now is turn the rotary stage, say every degree or two, and then simply map the power, the output power from the output coupler versus the angle, the actual angle. Not the angle I read on here, but the corrected angle. Once I graph it, I'll be able to figure out exactly where the laser stops oscillating. Where it stops, I grab that angle. I use the Fresnel equations in order to determine the loss, the reflection loss of the glass slide on each surface. And then I use a GTH equation incorporating that loss to determine what the small signal gain of the actual amplifier is. So I'll turn this 2 degrees, grab a power reading, turn it another 2 degrees, grab the power rating, turn it another 2 degrees, and so forth on one side of the glass until it stops operating. I'll do the same thing for the other side of the glass, and with any kind of luck, the two numbers, the two values for loss on either side should be approximately the same. Once we've measured that inserted loss inside the laser, the last thing we need to do in order to determine the GTH equation is to know the reflectivity of each optic. The easiest method is to measure the transmission of the OC directly and then calculate the reflectivity of the HR from measurements of powers of both the OC and the HR from this operating laser. Now the laser is already set up, so I remove the glass slide from the laser itself, and I'm measuring the OC power directly here. Be sure to take the standard precautions that you do when making power measurements. In other words, be sure to zero the meter correctly and compensate for those things like the blue glow that's coming out of the actual laser itself. Measure both the power of the OC over here, and it's in the milliwatt region, and then measure the power coming out of the HR. It's going to be in the tens of microwatts. Knowing those two powers, we can calculate the transmissions of these optics after I measure this one directly, and that'll be the final stage. For convenience, the easiest way to measure the transmission of the OC is simply to use the same mounts that I already used for the laser. So inside the laser tube mounts that were previously holding my plasma tube, I've mounted a small lab laser. This one's rated at 633 nanometers at a couple of milliwatts. I pass that laser beam through the OC and measure the power coming out. So I take two measurements here. I take a measurement of the power through the OC itself, and I'm getting a value of approximately 39 microwatts, and then I remove that optic completely to read the power of the initial beam, about 2.1 milliwatt, or sorry, 2.3 milliwatts. So by ratioing the transmission with the OC in place versus without the OC, I can then calculate the transmission of this OC optic. If I know the transmission, reflection is 1 minus transmission. If I know what the OC is, and I know the two power readings off the completed Heaney laser, I can then calculate the actual reflectivity of the HR itself. Now one wonders, if you're measuring the OC directly like this, why not simply measure the HR the same way? That is indeed possible, but the problem is the amount of transmissions of these mirrors. This particular optic has a transmission of a little over 1%. And so if I start with a 2 milliwatt laser beam here, I'm going to get approximately 20 or 30 milliwatts over here. That's a fairly easy thing to measure once you zero the meter properly, and you can get an accurate measurement like that. The problem with an HR is the transmission is on the order of 0.0001%. It's very, very low. And so the power you would be measuring here is nanowatts. It is possible to measure nanowatts accurately, but you'd have to exclude almost all light from this room, and you'd have to be very, very careful to zero the meter properly. It's far easier to use the method that we're using here in which case you measure this one directly and simply infer the value of the HR using the measurements of power from the HR and from the OC ends on that operating laser.